Hi, my name is Mike Kurdziel, and I'm an engineer with Point One Navigation. I'm going to show you a quick demo of our device profiles, which is a system that allows you to take advantage of our software-defined corrections network. So we have here our web app on the left, which shows our device and credentials and other things. And then on the right, I'm going to have a Ntrip client that is going to act as it is just on our network getting corrections. So you can see that it has message IDs, the station it's getting corrections from, the epoch and seconds, and information about the signals that it is seeing. So the first thing I'm going to show is the ability to change the correction rate of the corrections that are going to your device. This is really important because you may want to limit the rate to save bandwidth, to save processing power, to save CPU, and only give you what you need to be successful at your device. So we see here that the corrections are coming every second, which is very common. And then we go over here and we're going to create a new device profile. So we're going to call this correction rate. And we're going to enable this, and we can see that we have options here between 1 second between messages up to 30. So we're going to set it here to 10. We're going to save this device profile, and now it shows up in our list. We go back to our device, we go down here, and we can actually pick the device profile for our device. So we're going to change that from no profile to our new correction rate profile. And what we can see here, over here, is that they're still coming in at once a second. Once we apply that, we see the corrections stop, but they didn't stop. They're waiting 10 seconds before the next correction comes out. So this allows you to reduce those corrections to only what you need, to only the accuracy you need for whatever your device is doing. A common example for this is if you have a robot that is out navigating the world, it has kind of two scenarios. Either it's operating and needs high precision, or it is docked and does not. And maybe when it's docked, you want to reduce the correction rate. And we see over here that we went from once a second to now every 10 seconds they come out. Say now your robot goes from docked back to operating. We can go back and we can either create a new one called full corrections, and that's going to have the correction rate at 1 second. We save that. We apply it to our device, and we do this either through the web app or through the API, back to full corrections. And what do we see is that our correction picked right back up again without reconnecting, without reconfiguring, and it's automatic. This allows your cloud to talk to our cloud and your API to deal with our API so that when you know that your device is in a docked scenario, you can tell our network to slow those corrections down, to save bandwidth, to save power, and save money. And that's correction rate. The next one is called signal filtering. This is similar, but instead of changing the rate, we want to change what signals actually come through on the correction stream. So over here, we see a bunch of different constellations. We see GPS, Galileo, Baidu, and say we only want GPS. Maybe our device can only handle GPS, our receiver only configured for GPS, whatever the case. We know that's what we want. So we're going to go over here. We're going to create a device profile called GPS only. And we're going to specify the output signals. And you can see here we have the different constellations and frequencies and even messages within those. So we're just going to pick all of our GPS signals. Once we do that, we see we have this new profile and the signals that are on it. We're going to go back to our device and we're going to change to that profile. So this is GPS only. And what we'll see over here on our client is that the other signals are no longer coming through. It is just our GPS signals of L1, L2, and L5. And so that's a really handy way to make sure you get only the signals you need going to your device. Another feature is called required signals. So this is the opposite example of signal filtering, but instead you want to make sure that you're only getting stations that have the signals you need. So if we go back here, we're going to remove the device profile, and then we're going to go look at our map. And so we see we have two stations and our device. This is 1006, which is what we are connected to because it is the closest. And then we have this further one away, which is 3022, which is we're not connected to, but it does have this Galileo E6 signal that our current station does not. Say we need that signal. We're going to go back and we're going to create a device profile that is requiring it. So we go here and we say Gal E6. And then we're going to set required signals to that signal. So here we have Galileo and here we have E6. So we go over here, we save that profile. We see our device is still connected to the closer station, 1006. We're going to apply this new profile that requires this other signal. And once we do that, what we're going to see here is that the network switched over stations to this 3022 that has that Galileo E6 signal that we told the network that we needed. And so this is a really powerful way to make sure that as your device is moving through the world from station to station, you're making sure to only get stations that have the signals that you need and can use as you are connected to our network. Okay, another way is max baseline. Max baseline is the maximum baseline that you want to receive the single baseline signals from. Say that you need to be within 20K or within 50K to get the solution that you are looking for. And outside of that, it is no longer useful to you. Well, we can do that with a device profile. So we're going to start a client here that will show how far away we are from the signal. We're still connected to Galileo, so we're going to remove that. And then we're going to pick 1006. Here we are at 13 kilometers from our base station. So say we only want 10. We're going to go here. We're going to create a profile called max baseline. We're going to set the maximum baseline, again, from 1K to 150K. We're going to pick 10. And what that's going to do when we set it to our device is that the corrections will stop because we are outside of our maximum baseline for single baseline corrections. So there it stopped. If we decide that that is not what we want, we can actually go back and we can edit this and we can say, well, 10K is too short. We want 20K. That's more reasonable. Once we save that, what we see is that our corrections pick back up again. The network got the dynamic device profiles pushed to it. It adapted to the new setting and it said, well, this device is now within its max baseline range. So I'm going to produce corrections again because it is now within 20K. So that's a very powerful way to limit what your device sees to only what it needs. Another feature is what we call auto virtual RTK. So this feature allows you to go from our single baseline true RTK network to our virtual RTK network, which is virtual base stations. This allows you to balance the high precision of having single baseline with the improved coverage of the virtual stations of virtual RTK. So what we want to do here is we want to create a new profile called auto virtual RTK. And here we see we have a similar range and we can choose when we want to fall back from our true RTK single baseline station to our virtualized virtual RTK station. So we're going to set this limit to 20K and then we're going to go set it to our device. And then we're going to start a client that actually walks away from a station. So we see here, it is traveling a kilometer a second away. It is connected to that station 1006, and it is getting the single baseline true RTK corrections. Once it travels outside of the threshold we set in our device profile, we're going to see that change. So there's 19 and there's 20. And what we just saw is it went from that single baseline 1006 station to a virtual station 4012. This is on the virtual RTK network getting virtualized stations, which has a much broader coverage than our single baseline solution. Doing this allows you both the power and precision of having that single baseline station when you are close to one, and also the increased coverage of the fallback onto the virtual RTK network that has coverage much denser across the entire country. And another option that we can do here is datums. Datums are an important thing to surveyors and map makers and people that have coordinate systems that they need to work in and don't want to do things like translations in post. So what we're going to do is we're going to start a client here that shows us the position. So this is the XYZ ECF position coming off of the 1005 message. We're going to create a new device profile over here, and we're going to call it local datum. And over here, we're going to select override. So we see here is our ITRF 2014 global reference frame, and then also our local datum option, which will give you the local datum based on where your device is operating. So we're going to select local datum, and then we're going to go back to our device. We're going to change it to that local datum profile, and then we're going to watch the change happen. So we see here we have the position in our ITRF 2014 frame with a 43277, and then we have it switched into that local datum frame of 4129. So small difference, about 3 feet between the global datum and the local datum in this scenario, but that's very important for people that need that. And this gives you the ability to configure that and change that through the software-defined corrections network and not have to change device settings or reconnect or do translations after the fact. So this is a very powerful feature for those who need it. And that is our device profiles on our software-defined corrections network.